Yes, but I don't. Yes, yes.
So please tell me when you're ready, Philip, and I'll stop sharing this picture.
Yeah, I can say something. I guess I'm the odd man out here, coming from computer science, and I'm actually in the applied part of computer science, so software engineering. But my background is that I've been applying, I started with biologically inspired algorithms like evolutionary algorithms and genetic programming and so on in the 90s to try to improve how we build software systems. And then over the years, we've applied these type of modeling approaches to help companies like Ericsson, ABB, and so on to improve quality of their software development processes. Okay, great. Great, thank you. So, and more, we apply these type of ideas in. Oh, please go back.
Oh, sorry.
Yes, we can start here. And so more and more we apply these type of ideas in medicine. So we recently got some funding from Vetenskapsrådet, the Science Council in Sweden. One project for how do we test these type of models once we build them, and the other one for in hip fracture prediction. So we will compare existing sort of traditional statistical models with interpretable machine learning models. Okay, so today this is not so much about our own research. So I'm going to be, this is more like a meta talk. What are my thoughts on what are the benefits and downside of massive or big data type of machine learning versus more often smaller mathematical modeling? So next slide, please. So there are some very promising results. So we could argue that maybe we are seeing something like machine learning to the rescue in general here. So this is a much discussed paper, I think it's 2 years back now, where there's a huge list of authors on this one. So you can't see them all on this picture I've chosen. But this is a big team from Google Brain. And what they did was to build very large and complex machine learning models from very large scale big data. And sort of the novelty here is they claim it's a scalable and very accurate models based on deep learning. And they do it sort of without any need for understanding or harmonization or encoding or feature extraction. So that's the main thing here, that they sort of present the data in a fairly raw form to these complex modeling approaches. And it's really a lot of data points, as you can see here. And the end result is, so they predict many different things for multiple different diagnoses here. So mortality, the length of stay, and other sort of common target outcomes in medicine. And the area under the curve values here are often very high and state of the art. So 0.94 for mortality, length of stay is a little bit lower, but still quite useful and definitely higher than many existing results. So what does this mean? I mean, it's interesting, of course, it's kind of direct, but what's the effect on our understanding, and should we use these models, and what does it mean to do so? So next slide, please. And you know, I was very taken aback when I saw this paper, and reading the paper itself, I was very impressed. But over time, and if you look deeper into this paper, you have to question the bang for the buck, because there's a lot of compute that went into this. If you look actually in the supplementary material for this paper, you can go to a table there where they actually compare it to baseline models. And yes, it does beat a full feature simple baseline, but this simple baseline model is actually just a logistic regression model. So they had to, it's still a fairly complex model because they do represent many features to this regression algorithm. I'm not sure, it's not really clear if it's a lasso or something else. But in the end, you see that the area under the curve values here are, okay, it's lower, but it's at least it's close to the deep learning results that you have to sort of at least discuss what kind of trade-offs there are in using these types of models. So you see for the inpatient mortality rate, it's 0.93 as I've marked here for one hospital, compared to 0.95 for the deep learning model. And if you go down, you see a similar pattern. So it's slightly, so there's some benefit to this complex deep learning model, but it's a little bit unclear. What do we lose in using this? So next slide, please. And one thing you can definitely question here is, what are the costs of this type of complex model? Can we trust it? So if you look at the actual architecture they used, there are 3 neural networks that they actually put in an ensemble to get their predictions. So at first there's a special form of recurrent neural net based on an LSTM, so long short-term memory type of architecture, which is weighted. So there's a lot to understand and tune when just training that model. Then there's a feed-forward, more traditional model, but it's an attention-based one, and it's time-aware and so on. So there's, you have to understand a lot of different technologies and recent algorithms and training methods in order to train even one of these neural nets. And finally, it's maybe a more simple to understand neural net with boosted time-based decision stumps. And then they had to ensemble these 3 together to get to the final prediction. And of course, then there are many hyperparameters. So it's a little bit unclear, and it's also only in the supplementary materials, but it seems that they actually had different hyperparameters per hospital, which is a little bit, you can imagine the compute going into that. So, not only do they have to be in the inner loop of training the neural networks, they also have to sort of explore a quite multidimensional hyperparameter space just to train one of these networks. So, in the end, it's not clear actually what were the detailed network sizes, number of layers and so on they used, and neither do they report on training times. But it is very clear that this is going to be considerable, and it will have to be someone with quite a lot of resources. And today that often means Google, Facebook, or OpenAI and so on, to even take on the cost of training this type of model. And there's quite a lot of papers out there showing downsides to these type of models. And I think some of the presenters later today will talk about some of these studies showing that what has been found after we've trained a complex model like this, if we go and look at what kind of factors is it actually using, in many cases we can find that they are using operational features. So for example, an operational feature would be the time of an event rather than a physiological predictor, like the age of the person or the heart rate variation or something like that. And this is very risky because you can imagine if you train then on a few hospitals and then you move this model to a different context, what if the operational processes are different? There's a big risk in having models where we don't really know how these different families of predictors actually relate to each other and are used in the model. And it's one thing to check this, are there operational variables and predictors being used? But how do we then debug it, even if we do find out, right? So it's not so easy with these complex models to sort of tell them to not use a certain factor. And in particular for this type of model that they presented, where the data is presented in a fairly raw form, then it wouldn't really be clear how do we take out some feature that we don't want the model to lock onto, so to speak. Next slide, please. Yeah, this is going to be hard to understand from the PDF because everything is in one slide here. So
I can switch because I think I got the other one right.
Okay, if you have the keynote, that would be better.
Yeah, I'll try to do this.
Sorry about this.
This is the keynote.
Yeah, that's great. So it's 5th. Right.
Ah, okay, sorry. This faster. Like
this
that.
one, yeah. Thanks. Okay, so yeah, just click one at a time. Okay, so yeah, somewhere here, we can stop here for now. So there seems there can be kind of a dichotomy here, and it was also hinted at in Bernd's introductory comments about the questions for today. So on one side, we have to the right here, kind of a big, hairy machine learning. So this is, here I use the recent GPT-3, it's hard to say. So the largest, well, at the time, the largest neural network trained for language generation. So it's maybe not a typical one for biological or medicine applications, but there are benefits to having these large neural nets in most application areas. So you have on the right there a fairly complex sort of small structure being a transformer of many different smaller mini neural nets, and then you have a couple of 100 million of those replicated and in a certain structure, and then you have to train all of that for a particular task. So it's truly massive, and I think it's been estimated that the cost here was in the order of $5 to $10 million to train the GPT-3. And so we have that, and it has some uses, of course, and we it's early days, so we don't know how we're going to use them, but they're going to be used for sure. And then on the left, we have more traditional mathematical modeling or mechanistic modeling, where we can sort of posit a few features that we know or think are important, and then we put up some functional form for that, and we have excellent both theory and ways of training that or adapting that to something that we want. Okay, so click. So what are the benefits here? Of course, on the left we have something small, so it's tangible. We can discuss it easily. We can play with it. We can refine it. It's also very importantly kind of mechanistic or even causal. So we can posit what are the actual factors that determines our outcomes of interest or specific outcomes we're interested in. And both of these things together helps making for a more understandable model. So in some sense, this is what we know, what we're used to, and we can trust it in a sense. And if we click, we'll see some of the good things on the right side. So of course, here it's data driven, obviously. It can have massive number of features. So this can be a benefit, of course, if we don't know exactly which features are important. And most humans wouldn't feel very comfortable creating a very complex mechanistic model with massive amount of features. It will be a challenge, and in some sense it is always going to be, especially longer term, easier for an algorithm to do that and include many features in a nonlinear relation between each other. So you know, ultimately, hopefully there is more nuance and accuracy maybe on the right side. Who knows? So what are we going to do? And I guess what I will do today is give a few other examples of something in the middle. So is there some hybrid here? So explainable machine learning has been, of course, one proposal here. There we still build the complex model on the right, but we try to somehow find ways of explaining what it is doing, so we can sort of regain some of the understandability and trust on the left-hand side. And what I've been using lately is interpretable machine learning, which is a little bit different. It's more like a regularization in traditional terms. So we force the machine learning model to be small and understandable, and then we still train it in a data-driven fashion to hopefully find some hybrid between the two. I will also briefly mention AI Feynman. Maybe some of you have seen that. So that's a hybrid machine learning model for symbolic regression of physics models. So it's kind of interesting what it's been doing there. Yes. And of course, there's a whole field of causal discovery, and maybe less ambitiously called invariant models. So this is models that will stay the same in different settings of the system you're studying. So they are invariant under some change of setting or mode of the system. And they are clearly related to causal discovery, because if you can discover the causal structure of the system, then that will tell you what should go into the invariant model. Yes, click again. But I will not speak so much about the invariant modeling, but I will briefly mention universal differential equations, which I think also Philip had at the end of his talk. Yes, next one, please. So yes, and this area in the middle is maybe something people can call data-driven interpretability. So a big hero of mine recently has been Cynthia Rudin. So she's a statistician in Duke in the US, and she had, and I really found her, I knew about her from before, but this paper is a fairly recent one. I think it's 1 or 2 years back, and it's garnered a lot of interest. And she basically was fed up with the fact that people were using these big, hairy machine learning models. So she basically said we should stop doing this. And she has a very beautiful argument in this paper. So if you haven't read it, I urge you to check this. And she focuses on high stakes decisions. So sort of safety critical areas, like in the legal context or in medicine and so on. And we should use interpretable models instead. So next one, please. And I mean, her argument basically rests on the fact that currently the hyped machine learning models are often black box. They are opaque. They are difficult to understand, as I've argued also. And yes, click. And so she says that what's the consensus today seems to be that the learning performance has to go down. So learning performance is on the y-axis here. And as if we want better explainable models or interpretable, understandable models that we can trust, we have to pay a price in lower performance. But what she argues is that even on a fundamental theoretical level, this is probably a myth. Because if you go to sort of pack learning and sort of the mathematical foundations of machine learning, there are several results there that that indicate that, you know, the functional class that you're looking for, and where you're searching, the functional form where you're searching for a particular model, if that is expressible enough, there are plenty of models in there, and there should be ones that have the learning, the performance and accuracy levels of close to optimality. So there doesn't seem to be a theoretical fundamental limit to this that forces this degradation in accuracy if we go for smaller and more interpretable models. Yes, please, next. Yeah, so possibly this is a myth. So let's look at a few examples. What's happening in this field of explainable or interpretable machine learning? Yes, click. So here's for a language model. So it's maybe not a typical one for biological or medicine applications, but increasingly it can be, because we're learning from sort of the notes from doctors and so on. And this is at least a few years back, this was kind of state of the art. So this is using ideas from LIME, which is like an add-on generic method to add and explain what is affecting the prediction of a often complex and large machine learning model. So here, the machine learning model is some kind of binary predictions. It's predicting a 1 or a 0 from these short sentences. I think it's from Twitter tweets, text from tweets. And LIME in this case is then applied once you have trained your deep neural net for language classification here. LIME can go in and basically it reruns many times and changes things in the input to see which parts of the input is more or less important in reaching a certain prediction. So you see in green here is the more green a word or part of a word is marked, the more it's contributing to the specific prediction. So somehow the fact that we mention me here in the first sentence is strongly adding to the prediction of this being a 1 here. I don't know what they were predicting, maybe political tendency or something. Further below, you have that the really in the last sentence is then active in helping this become a 0, the other class here in the prediction. So this is kind of a typical way that explainable machine learning works. So it's kind of an add-on step after you have trained your model, that you use it typically by running it multiple times and changing the inputs to create more information about what's going on and what is causing the model to give a certain outcome. Next one, please. And when it comes to images then, which is heavily used with neural networks, of course, if you have some kind of image classification system, and you can click next one, you can use something called saliency maps to see which part of this image. Basically, it's a heat map looking at which parts of the image are contributing more to the specific class. So what Rudin does in our paper is show that saliency maps doesn't really help, because even with a model that predicts the wrong class. So this is actually a picture of a Siberian husky, as you see in the middle there. And in the middle, you see the saliency map for that prediction, Siberian husky. If you actually make changes, small changes to the picture, so that the network is predicting that this is some kind of transverse flute. I don't know what type of flute that is, but it's probably not a Siberian husky, at least. You see that the saliency map doesn't really help. It's just indicating a slightly less different part of the image as now helping us predict this is some kind of flute. And so she's arguing in this paper that many of these sort of bolt-on explanations doesn't really address the key problem, which is that any type of explainable machine learning that happens after and in addition to the actual model can only be a summary in some situations, and they cannot really fully explain what's going on. So it's going to be an approximation then of what the big, hairy, large, and opaque model is doing. And this is always going to be a problem with these type of solutions. Okay, please. If we look at the other side of the coin, so more interpretable models. So this is where Cynthia Rudin and her group and a lot of recent work in machine learning has focused. So here we are not trying to bolt on an explanation to a large and complex model. We constrain the model itself to be simple so that we can, in this case, this is the full model. So this is a case of in the legal system in US, judges can use today, or are using today, machine learning models to help predict if a convicted felon is likely to be arrested again within 2 years in this case, or not. So there are actually opaque, large black box models being used for this today, and Rudin has gone into and used data sets and studied, can we create interpretable machine learning models, and what price do we pay for doing so? So this is using their Correl's algorithm, where you basically give it a budget. How large can the model be? And then it's given certain assumptions, it can find the best, the most accurate model within that size budget. So this is very interesting from a medicine and for any type of safety critical use of machine learning models. But you can also see the benefit in a scientific context, because maybe we can sort of, if this can help us find the more causal and the actual more invariant models, we can learn about a complex scientific situation and a data set by applying these type of interpretable machine learning techniques. So if you click, Philip, you'll see that the comparison here to the COMPASS model. So COMPASS is a black box machine learning model, which is a commercial one. So this is being used in several states in the US. And it has more than 130 different factors. So you basically have to collect all of these factors and input that into the black box model. And the questions you have to answer are questions about your parents' prior legal record. So there are many different problems with this. And when they used the Correl's algorithm and gave it a very small budget here, the full model is the one on top, and it has a similar accuracy, and it doesn't use any of these very sensitive factors that was used in the commercial model. So it's free, it's open source, it's transparent, and you can restrict it to only use some features that you want it to use. Okay, next one. So this is called a rule list model. We don't need to talk about that. You can of course have different shapes. Here's a different one. This is interesting from an applied perspective in medicine, because scoring systems are currently quite widely used in medicine. So a scoring system is often what medical research has created to guide treatment and diagnosis already today. So in the scoring system, there are several factors, in this case 5, and you basically check each one, and if it's true, you add up the points on the right. So here it's applied for the same legal arrest prediction problem as in the previous slide. So you basically say if the person in front of you has, say, 6 prior arrests, both feature 1 and 2, or rule 1 and 2 will be true. So you will get 2 points for the first 2, and then you go on and you add these up. And then your final score can be used to predict the risk of a future arrest. So this is a scoring system model, and so it's slightly different than a classification model. But you can see that this is a quickly expanding field, and depending on what you're after and what you need to use, there will be plenty of algorithm methods to do this for the form you're interested in. So next one, please. Rodin's group have also tried to use sort of hybrids between explainability and interpretability. So here they actually train a neural network, but they force the network to be very explicit about which training images is it using in its prediction. So for a new image that's going to be classified on the left here, the system and the architecture of the neural network is set up so that it will point to different parts of the new input, in this case the picture on the left, and it will link them to which parts of the training images that it has found a good match with. And this, then you get more context and example-based saliency maps that can act as a explanation. And here you see that it is a mix. So we're not purely bolting on the explanation after the fact. We're actually constraining the form and setup of the network itself so that it can give us an explanation or be more interpreted from the get-go. So yes, next one, please. Okay, next example. So now we looked at a few examples in the interpretable or explainable ML field. Now for something quite different. So this is the AI Feynman. I think it's from early this year. So if you haven't seen it, I think it's an interesting paper. So this is from Max Tegmark and Udresco at MIT. And this is for sort of a classic problem of symbolic regression. So symbolic regression is to find the actual functional form, say like a physical law, given a data set of examples sampled from a specific instance of that system that you're studying. And of course, symbolic regression is interesting. It's been done in many different ways through the years. And the nice thing is, of course, that it has a more free functional form. So the space of possible models it can fit or find are often huge in this case. But what they do in this paper is to combine it. So they basically claim that in a particular domain, like in the symbolic regression of physical equations, we have a lot of knowledge already. So how are we going to utilize that and hybridize symbolic regression and use modern machine learning in order to find the actual physical laws for given a data set? So next one. So the AI Feynman is a hybrid system, and we don't need to go into all the details here, but if you click one by one, Philip, it exploits many different domain-specific properties that we sort of know of the domain of finding physical laws. Is that we can do dimensionality analysis. We know that all the features that go in and the output that we are after have certain physical units, and we already know how they relate to each other. So things like mass, energy, length, velocity, size, and so on. So we can constrain the whole search of a particular model by using, we can reduce the size of the functional forms that are relevant based on this. We also know that most physical laws are low order polynomials, so we can use specific solver algorithms utilizing this fact, so we don't need to use this very free form machine learning search in a huge space. There's also compositionality, and if you click on, Philip, I think we have 6 things here, so you can stop after the 6th. Yeah, here. We have compositionality. So what they do there is that they train neural networks on the data, and then they look at, can we decompose, does there seems to be like a particular form to the neural nets that are found, so that we can have like a sum or a product of different smaller problems to solve. So they sort of recursively subdivide the regression problem based on studying neural networks that are trained to approximate the original problem. They use, of course, smoothness, that we know that the behavior of the function we're looking for is going to be smooth for minor perturbations and so on, and then symmetries, also they have specific ways of using that, and separability in sums and products. And this they do recursively. So as soon as they prove that there is some symmetry or separability, then they will subdivide the problem and now rerun the algorithm on the two sub or multiple sub problems. So it's a very interesting way of, given that we already know a lot about what we're looking for, how do we mix between a more data-driven approach and including all this prior information that we have. Next one, please. And the outcome is pretty promising. So it can solve about 73% of something called the Feynman symbolic regression database. So this is basically this is samples for all the equations in the Feynman lectures, the famous physics lectures he did. So basically the tasks are given samples from all of these equations in his lectures. Can we recover the actual laws based on just samples from the system? And you can see here that it doesn't always work, of course, but the solution times are fairly small given this type of algorithm. I think the one on row 6 there is a more complex expression, still solved in 30 seconds. The second to last takes, well, you know, I think they gave the algorithm maximum 2 hours on each task, and this one is about half an hour to solve the next to last one. Also very interesting here and typical is that this is much more data efficient than typical machine learning. So they need very few samples compared to training these large, big, hairy neural networks. Okay, next one, please. Okay, final example of you know, where this hybrid area is going. I think universal differential equations is maybe the most intriguing for scientific machine learning. So if I put the abstract here because all of it is worth reading. If you just click once, Philip, I've marked some things here. So really, I mean, what we're after with the scientific or mathematical modeling is typically that, you know, a small model capturing the causal structure of the system will be worth 1,000 data sets, right? And if you click once more, so what they say here is that we want these type of scientific models because in some sense they better reflect reality and you know, we can control them and so on. But oh, please go back. Sorry. However, you know, so machine learning can approximate a lot of this and directly learn the entire set of nonlinear interactions from data. This is great, right? We want that. But how do we constrain that? How do we get simplified models without requiring a lot of big data in a sense? And they introduced the universal differential equations here, which is a hybrid. So next one, please. And this really, like, this has already been used. I'm not sure of the example that Philip had on one of his last slides, which type it was, but there's like a continuum of different approaches here. So if you click a little bit one by one, there are like physics-informed neural networks where you use partial differential equations in the cost functions, but you're training a neural net. So I'm not sure, that probably wasn't what you showed, Philip. So we can include prior scientific knowledge by constraining the loss or cost function. And this can lead then to more data efficient learning. We can have fewer examples and still train a neural net here, if you click. But there's still a lack of interpretability because the shape of the model itself is still a neural net in the end. So, you know, we get this problem of explainable machine learning. On the other side, we have neural ODEs, which where we use scientific mathematical structure as the basis for the ML. So here, basically, we have a differential equation, and the neural net is on one side of it, and it's trying to. So maybe this was closer to what Philip showed. And if you click again, Philip, basically there will be some matrices involved here. So a more traditional neural network is used as one part of, or in the, you know, is used in one part of a more classical differential equation. And if you click, the good thing here is that a neural network is a universal approximator, of course, so we can approximate any sufficiently regular differential equation this way. But if you click again, it's hard to incorporate known mechanics or relations in here, right? So on this continuum, none of these prior solutions really has all the things that we want to combine. But if you click, the universal ODEs, UDEs have this. So they combine the mechanistic models with universal approximators. So instead of having the whole one part of the net of the equation being a neural net, you can combine it much more in a much more fine-grained way. So it's semi-mechanistic, and it has the potential for data-efficient learning. We can incorporate known mechanics if we know something about parts of the system. If we have prior knowledge there, and click again. And higher interpretability. So stop there. So here's an example then. So if you have the classic Lotka-Volterra differential equations on top there, what you can do is to say that, okay, I know something about this system, but I don't know the full extent of every interaction. Or, you know, for maybe we have model misspecification. So we can have some additional neural network being part of these differential equations, and we can train them inside of this, and you know, see, basically mix the benefits of both. So this is very interesting. Yes, click again. And here's some outcome of this, and they really show that you can do very data efficient learning here. So if you look at on the bottom there, the graph number C, you can see that with very few data points sampled from the actual Lotka-Volterra there, they can get excellent predictions from these systems. And we've already seen this being applied, I think already in the spring. This type of UDEs have been applied for COVID admissions, you know, patient admission modeling and so on. You know, it allows this mix of approaches on this continuum. So next one, please. So in the end, is this a dichotomy, and do we have to choose either one? No. So I have my feeling is similar to Philip's and Bernd's earlier here. I view this more as all of it is a toolbox. So there's no real conflict here, and it's very likely that we're going to see more and more hybrids. We want to be able to do this. And why? Yes, if you click, we'll see why. Because when we have a lot of knowledge of the system, or we have existing theory that explains what should be important in a particular system, we want that to be part of the final model. On the other hand, when we don't know so much, we have maybe lots of data, but we're not yet clear. Let's say COVID early on, we didn't really know what will actually affect the number of admissions, or what will actually explain which factors are important in increased mortality in COVID and so on. So there's really a spectrum here, and we need to have this toolbox of different solutions in order to pick the right for our situations. Click again, please. If we are on the more safety critical side of things, then we really want to push for a simple, understandable model, because then we can study it and see its failure modes and see the problems with it and more easily address them. But there are many applications where accuracy is primary. So if I'm trying to optimize the number of clicks I get in my mobile app game or something like that, it's less important that I really understand the system. I mean, a 1% increase in accuracy might be the right choice there. So it really depends on the situation. For understanding causality and in scientific cases, we probably want to push more for the left-hand side, and then the hybrid type of solution are more likely to be helpful to us. But of course, we're going to use everything on the spectrum to reach our goals. I think I have a few more if you click again. Oh yeah, and you stop there, yeah. And one thing that I think is a little bit maybe novel and comes more from my area in this is that you have to consider the target automation level. So it's not only about how much data do you have versus how much knowledge you have, or the basic setup of the domain you're studying, how safety critical is it, and so on. It's also about the target automation level, and I'll show a little bit what I mean on the next slide. Okay, I'm sorry, I'll finish up now. So, this is from the aerospace industry, that when you create an automation system, you have to consider what kind of level of automation should it provide. So on low levels of automation, the computer offers no assistant. The human must take all decisions and actions. And as we go up on second level, the algorithm or model just gives you a set of decisions that you can select from. But as we go higher up, we come to level 7, 8, where the computer takes the decision and only informs the human. And on level 10, we have basically a Terminator style, if you click, a solution where it's ignoring the human. And it really is different depending on what type of system you're building. This should be different. And depending on where you need to be on this spectrum, this will also affect the level of understanding you need to have. So final slide. Yes, just a summary. So is there a dichotomy? Maybe, maybe not, probably not, I will argue. And one problem is that we're not yet sure, but there are many indications that we need the complex data-driven machine learning models, but it could be a myth that we have to pay with lower accuracy. Click again.
Sorry.
Oh, okay. We looked at just two examples, was AI Feynman and these UDEs that are clearly some kind of hybrid of different types. And finally, I think we should view this as a kind of a toolbox. So sorry for the fuss and for using a few extra minutes. Thank you.
Thanks a lot, Robert, for this very interesting talk and fascinating topic. And we are a little bit into our coffee break here, but I would like anyway to leave room for at least one question if somebody has a. So please raise your voice.
Bent, there is a question in the chat here from Hitesh.
Hitesh has a question. You can maybe say it yourself.
Okay, so thanks for the talk. It was really interesting. I quite like some of the examples. So I guess having a mixed background of math modeling and statistical modeling, I guess my question is, in your toolbox, you never really mention anything about statistical modeling techniques in general, right? So where does that fit in your knowledge toolbox? So, because for me, that is what I do on the right-hand side. So when I have data, I build statistical models, not machine learning models.
Yeah.
So do you make that distinction? And yeah, it's just a thought, really.
Yeah, I mean, I'm fully on your side there. So I mean, the first thing I will do is to, when I approach something where there's a lot of data, but little knowledge, is to pick out the lasso and see what will it do here, and get a feel for that. And many of the interpretable machine learning algorithms today, they reuse sort of classical statistical modeling techniques and often run them in a loop. So there's this, I'm not sure fully what the technique is called, but basically where you use the lasso as kind of a variable selection, and as soon as you have found a model, you sort of start picking out the most important features and then rerun the lasso to basically use that as the first step in building your interpretable machine learning model. So I would put that's probably in, it's more on the right side, but it's often used in creating this type of interpretable models. I think that the new thing that happened this year was that more classical computer science and mathematical optimization came into the interpretable ML sphere. And so now we are using SAT solving and so on to really create, this is the best model that we can find given this size.
Okay.
So yeah, it's definitely in there. Thanks.
Thanks. Any other question? In this case, let's thank the speakers this morning in the way I suppose we do now with our hands, and go for a coffee break. And we join here again in 15 minutes, please. And so that would make it a 11 then, I guess. And so please rejoin us again after the break.
Just wait for a couple of more seconds here. Okay, welcome back everyone after this refreshing break here. And we have two speakers before lunch, and the lunch will be a little bit shorter than announced. So we'll plan to finish at 12:15 the latest. So first off, we have University of Manchester. He already introduced himself briefly as one of the questions to Robert before. So please, Hitesh, small models for big data.
Thank you very much. Thank you for inviting me. I quite enjoyed the previous talk. I apologize, I missed Philip's talk, but I'm going to probably repeat one or two things that Robert said. I didn't know what he was going to talk about, I guess. So apologies for that. I'd just like to acknowledge some people who basically one person definitely had a big influence on everything that I do these days over the past decade, really, and another collaborator of mine. So David Orell, who I work with as part of my consultancy thing. I'd like to thank him. He's really introduced me to a lot of forecasting methods. And generally, he's introduced me to what does prediction actually mean, and an uncertainty, etc. And some of his books are really quite a good read. And James Yates for some of the review of some of the slides that I put together. So we've actually written a perspective piece in the Journal of Clinical Pharmacology and Therapeutics that basically covers a few of the examples that I'm going to go through. And these examples are kind of taken from, I guess, my two strands of my life. So one strand of my life is the academic side, where I kind of work with the National Health Service, in particular Cancer Research Hospital. And the other part of my life, which is part of my more industrial upbringing, involving the pharmaceutical industry and biotech. So you'll see a mix here of things that are related to the industrial setting and things that are related to the clinical setting. But hopefully you'll find them of interest. So I guess for me, I've never really understood what the term machine learning really meant. That's why I always tend to put it in quotation marks. A lot of the time I do see people call sort of statistical modeling techniques machine learning, so I usually get confused. And I guess for me, for healthcare and for basically the drug development applications I'm interested in, uncertainty does matter. It matters a lot, and I'll take you through and explain the different sources of uncertainty and how I'm not overly always been convinced that whether machine learning techniques can really handle some of these levels of uncertainty. Then I'm going to talk about some of the examples of the pitfalls of applying machine learning. So like I said, a lot of my stuff is clinically based at times. So I'm going to talk about some of the papers on using electronic health record data and the issues. And trust me, there are a lot of issues that people have not really discussed. We're going to talk about reoffending risk, but we've already seen that from Robert's presentation. So maybe I'll just touch on that briefly. I'm going to talk a little about financial predictions. And then I'm going to talk about something what I call the perfect con. So please do take this tongue in cheek. And essentially what I'm going to highlight is how you can actually combine mathematical modeling and machine learning quite easily actually and create wonderful papers that will quite easily get you into high impact journals, but in general don't really provide much. And I've got quite a good example of that. Hopefully you'll agree when you see it. So I guess there is, so this year I was at the annual Biostatistics conference, which also happened to be virtual, and their keynote or their plenary session was actually on machine learning versus statistical modeling. The reason for this is there is actually a war brewing between the machine learning community and the statistical modeling community to a degree. So if you're an avid Twitter or social media follower, you will see some of these sort of statistical modeling experts really having a go at the machine learning community and vice versa. And I guess one of the problems here is that I guess one of the things that we've discussed in a lot of these discussions is the ability to handle uncertainty. So I guess with statistical models, it's quite easy. You generally specify a probabilistic model for the data. So actually it's quite an easy thing to do within the statistical modeling framework. However, is that definitely true of the machine learning community and the machine learning methods? I'm not so sure. And I think this is kind of irrelevant. So this ability to handle uncertainty is really important, I guess, in the industry that I work in, which is generally related to pharmacology and healthcare data, where essentially there's so much uncertainty, it's beyond belief at times. And there are many, many articles on the problem of reproducibility within this field. And this kind of gets to the crux of the problem. And so one article of quite interest to me a while back was this one called The Economics of Reproducibility in Preclinical Research. So this is predominantly based on what was happening in terms of the pharmaceutical industry, etc. And I think there was a nice quote in here, right, which tells you one of the problems we face when we want to use lots of literature data, mine it, to try and use learning methods to mine this data and then use it to create knowledge graphs, etc. So use some of these complex techniques to look at the historical data. So the analysis of the past studies indicates that the cumulative total prevalence of irreproducible preclinical research exceeds 50%. So basically, what does this mean? Resulting in approximately $28 billion a year spent on preclinical research that is not reproducible in the United States alone. So we have a problem. We have a huge problem of reproducibility within the pharmaceutical industry. And this is kind of important when we're thinking of applying some of these more complex methods to the data sets we have. Can you trust your dependent variable, basically? So thinking about data generation, so thinking about applying sort of, I guess, machine learning or complex sort of prediction techniques to problems. So let's consider things like finance, actually. There's a nice example. What was the price of stock X on Monday at midday UK time? We know what that is, right? You can go and look it up. We have extremely good precision. There's no bias. It's good, right? It's a nice dependent variable. Imagine you're in marketing, did you buy a newspaper on Monday? Well, hopefully that's pretty clear too. The degree of uncertainty around that endpoint is not high. Reoffending risk, does the person sat next to you have a criminal record? I hope in this room nobody does, but anyway, you can see the thing here, right? So there's a degree of certainty around these things. There's little uncertainty in the above, right? And missing data really isn't much of an issue either, especially in the finance industry. You've got reams of this stuff at very, very high resolution. But is that true in healthcare? So my background is predominantly in cancer research and in oncology. And actually the only real well-defined endpoint, as people say in the UK, taxes and death. And so death is one of them, and death in oncology is quite a well-defined time point. When a patient's died. However, what's interesting, that's about as certain as you can be. You know when they've died. However, what they've died of kind of isn't always clear. And there is uncertainty in this. And when you work with electronic health record data, what you tend to find is that people will go for the easiest click box option when you're filling in death records. So do bear that in mind. You clearly do have certainty on when they died, but you probably don't have much uncertainty on what they've died of. And there's chances they'll pick more than one option. And this is because we don't really have a mechanistic model of death. We can't really factor out exactly what did cause the mortality. So one other thing that I'm interested in is in cancer is measuring the levels of tumor, right, you have in a patient over time. And there is uncertainty in this, right? So imaging is by no means perfect. It has a certain limit of quantification. And there's uncertainty in that too when you have radiologists. If you were to take two radiologists and ask them to look at the same scans, they would not be 100% concordant. So there is uncertainty. So if I was building a machine learning model to regress against tumor volume or some sort of level of tumor burden, there is uncertainty in that measurement. So I need a way of handling that. Measuring biology, if you think about omics data sets, these two also face problems, right? In terms of the endpoints, the input variables, so measuring this stuff. And we use antibodies a lot, right, in biology so that's strange, right? I mean, how many other fields do you know? I mean, it's quite interesting that we use biology to measure biology. This just creates a whole another level of uncertainty. And if you're a statistician, this is the point where you probably get sweaty hands and start to really panic about what's going on. So uncertainty is vast, right, in both the inputs, so things like omics data, and the outputs, the things you want to regress against. So we have uncertainty in our independent variables or exploratory variables, and we have uncertainty in our dependent variables. So it makes it quite hard, actually. So we have a lot of that, which you don't necessarily see, I guess, in other areas where there is a lot less uncertainty in the things that you're interested in. So I'm going to come back to this concept of reproducibility in science itself. And Nature did this survey of scientists across areas of sciences and asked, well, is there a reproducibility crisis in science? And the answer is yes, there is. So what they did is they interviewed 1,500 scientists from different fields. And they asked about, well, have you ever failed to reproduce an experiment, either your own experiment or someone else's experiment? And you can start to see some of these charts. It's a bit of a problem, right? So let's just look at your own experiment. So you can see that in biology, 60% of these scientists that were reviewed said that, well, actually, they failed to reproduce their own experiments. Generally, it's hard to reproduce other people's experiments, but actually, the ability to reproduce your own experiment is actually quite a problem, right? How do you deal with this issue, right? So if you're sat there working with lots of healthcare data and you know that you're essentially mining lots of literature data, how do you know you can trust this stuff? It's really quite hard, actually. And I guess this leads me on to a rather interesting point, which I've started to learn, is that machine learning methods are actually quite good at finding signals in random data. And a nice example of this is I'm quite interested in data reduction techniques. So normally I sometimes deal with at the hospital quite high dimensional data. So my go-to methods are usually, well, it's a single method. It's usually principal components analysis to try and reduce dimensions. But I know there's other methods out there, right? Some quite interesting sort of nonlinear methods, for example. And TSNE, so T-distributed stochastic neighbor embedding is one of them. But I know some of these more complex methods, which are quite useful for taking high dimensional data and reducing it to 2 to 3 dimensions. They do depend on certain parameters which you have control over, right? So for example, the tuning parameter in this method. And actually there was a nice blog post I came across, which highlighted here, which essentially highlighted how you can use some of these more complex methods to take random data and find structure in it. So it's actually, you can use complex methods on data to find structure in data when there really isn't any. So that's quite interesting. So that was one thing I started to learn when I started to look at some more complex methods to try and look at dimensional reduction techniques for data sets that I've been interested in. So that's interesting, but we do see a lot of positive reports, right, on machine learning, right? We see a lot of reports on machine learning, people comparing themselves to in the healthcare industry compared to healthcare professionals, saying, oh, look how well the machine learning model performed, etc. But is that really the case, though? So I use phrases like rig. So this is basically meaning, well, how do you cheat in a machine learning versus scientist experiment? So there's a nice article, and I quite like a guy called Martin van Smeden, sorry. He has some interesting viewpoints, and they're quite worth listening to. So this was a nice set of articles. So there was an original investigation, which was around using deep learning algorithms for detecting lymph node metastases in women with breast cancer. And then they, biostatistics group, kind of wrote a riposte to this original investigation. And essentially highlighted three main issues, right? So this is tends to be a common issue when you're doing these comparisons of people versus machine, really. So one of the key first issues was the physicians were not given all the information they usually receive to making a decision. So basically, the pathologists here were not given access to immunohistochemistry data, which they would normally use. So data they would normally use to help them to make decisions about cases that they are uncertain about. So they weren't given this information. And chances are the reason why they weren't given this information is because actually this is probably quite hard to quantify for the machine learning algorithm, of how you'd include that. The output generated by the algorithm and physician were actually measured on different scales. And actually what you should do if you want to compare, you should measure on the same scale, right? So the model was giving a probabilistic output, whereas the physicians were given a 5-point scale. So is that fair, comparing unlike with unlike? You could also argue that there is over-optimism in the performance of the algorithm, and it was hard to avoid, really. So in this original paper, they had 390 teams, 23 submitted 32 algorithms. They compared those 32 algorithms, and they chose basically the best of that, right? Versus 11 random pathologists that they could find, right? So they're not really comparing the best versus the best. They're comparing the best that they can do using the algorithms versus whatever pathologist you can find, right? So are these really fair comparisons that we're seeing in the literature? And I think this is something to be wary of when you're reading a lot of these sort of competitions where you see people comparing machine learning versus scientists, or machine learning versus humans, basically, in general, in different areas. Another example I've come across, which I thought was quite interesting, is in terms of using electronic health record data for prognosis prediction. So this was a nice article where they actually highlight that the data generation process is actually more predictive than outcome than the actual value of the test. So this was a large data set where they were trying to predict survival of patients from a essentially electronic health record database. So this would include people who come into emergency wards, right? Or include people who come in often. And generally what you know is that if you're coming into a hospital in the middle of the night, clearly you have a serious problem. And what they found actually, which I thought was quite interesting, is that in majority of these cases, the actual lab test values added nothing to the survival prediction. What was more important is when they came in and how often they came in. So if you're coming in quite often into the system, clearly you have a problem that's causing you quite some distress. And if you're coming in quite often in the middle of the night, clearly this is quite an important problem. So this is just it's quite an interesting article, but yeah, it tells you about some of the biases and the problems that you face when you're throwing algorithms at electronic health record data without really understanding the data generation process. And I think that's one of the points I wanted to get across here. Understanding the data generation process is actually really quite important when you're working with large data sets, I think, especially in the healthcare sector. We heard this before from the previous speaker, so apologies for re-mentioning this. So this was, again, a nice article about the accuracy, fairness, and limits of predicting recidivism, so reoffending risk. And I thought the abstract pretty much summed it up to me. To be fair, in the sense, I guess this is the last few sentences, actually. So initially what they found is that, that the widely used commercial risk assessment software was actually no more accurate or fair than predictions made by people with little or no criminal justice expertise. So I thought that was the important aspect of this, is that you could actually just take people and ask them themselves whether or not people with no actual experience in law to be able to classify patients as classify people as whether they're going to reoffend or not, which I think is what led them to believe that you could actually come up with quite a simple 2-feature classifier in the end, rather than using this industrial made sort of 137 feature machine learning algorithm. So I think this is one other important point, is to always benchmark. So don't just jump to the most complex approach possible. You should really think about using a multitude of models just to make sure you actually are getting some degree of extra benefit from using more complex approach. So that was one. I also have a bit of an interest in finance prediction. I've been following this through a friend of mine who I mentioned at the beginning. And sort of artificial intelligence and machine learning methods have been used actually for quite a long time in finance. So they've been used to make decisions about what to invest in and what not to. And there was a nice article essentially a couple of years ago that looked at, well, how well do these things perform? So there is actually something called a Eureka Hedge AI Fund Index. And this basically tracks people who kind of use machine learning algorithms to make decisions on what to fund and what not to fund. And what was interesting is the gains they were getting, right? So they were gaining roughly 7% a year for the past 5 years at the time when this article was written. Whereas if you just invest in the index itself, you would actually get a return of 13%. So you'd actually do better if you just invest in the index rather than using a complex model. And I guess in this article, what they did is they talked to some key opinion leaders and key people who've been using some of these approaches and other people who are skeptical of them. And they said, well, stated some quite interesting quotes, right? So they mentioned that machine learning algorithms will always identify a pattern, even if there is none. And that beating the collective wisdom of the crowd is much more difficult than recognizing facing or driving cars, right? So my person in the interview says, well, my dog can recognize faces, he says. So my teenager daughter speaks 3 languages. And basically said, well, I wouldn't trust any of them to manage my savings, right? So you got to be a little bit careful. And you really do have to be careful when you're using these methods. Decisions sued one of these hedge funds for where they didn't disclose they were using AI automated trades. I think it says my connection is unstable on my machine, but hopefully you're still seeing this. That they basically, the investors sued an AI hedge fund because they were disclosing they were using AI methods, and this cost them a load of money basically. So just to be wary. So those are my sort of case examples that I was going to talk about regarding examples I've seen what I thought were quite interesting. And they're summed up in that article that I put a link to at the beginning of the slides. What I'm now going to talk about is a very specific study. And essentially what I'm going to give you is a step-by-step guide on how you create the perfect math modeling machine learning study to get yourself a publication in a high impact journal. Again, like I said, this is slightly tongue-in-cheek, so hopefully you'll take it in that way. But it does highlight a problem, and hopefully you'll see what the problem is. So what would be the first step you would need to do to be able to combine a machine learning and mechanistic modeling exercise? Well, the first thing you would need to do is actually find the solution. So what you want to do first is find a simple solution that already exists. And so the example I'm going to talk about is in pharmacology, where one of the things we're interested in is when we have a new drug, we would like to predict, for example, a certain type of toxicity that could happen in the clinic in patients. So the toxicity we're interested in is something called torsade de pointes, which essentially involves your heart signal not functioning properly, right? So it's a cardiac toxicity. So in the pharmaceutical industry, one of the things that we're interested in is, well, can we predict whether a new molecular entity, so a new drug, is likely to cause this cardiac toxicity in the clinic as early as possible? And there's many people that have been looking at this. So what you're looking at is a pharmacological effect on certain proteins. And these proteins are called ion channels. And you have information on the effect of the drug on the individual ion channels at what we call an early stage in drug development. In the preclinical stage, you want to make a prediction, like I said, in the clinic. And so there's lots of interest in doing this. And this was an original paper where they took a reasonably, what I would call a large set of sample of drugs, but for most people, this is probably not a large sample, of 55 drugs where they have information on the input behavior, input information, which is information of the drug's activity against a specific ion channel. And they then try to predict or correlate that to a cardiac toxicity output in the clinic. And they found a simple linear model actually worked well. So the point here is that there was a simple solution that existed for this example, and it existed quite a while ago, I would say. So this is in 2013, this is 7 years ago. So then the next step you need to do is, there was a simple input-output relationship, but to make your paper sound better, you might want to try and find some more drugs. So what someone had done, and we'll disclose the paper coming up quite soon, is that they then searched for more drugs to maybe add some noise to the data set, right? But that a simple model will work quite well. So in this previous paper, for those of you familiar with ROC AUC values, they were getting values of 0.95, for example, right? So the area under the curve here was around about 0.95 using a linear model. So you want to add some noise, right? So you try and search for the drugs that have already been previously assessed. So you'll add that to the mix to increase your sample size. So what do you then do? Well, then you need to go and get a mechanistic model, right? That kind of represents the biological situation you're interested in. So I said here that we're interested in the cardiac toxicity. Well, we do have lots of mathematical models of cardiac cells. And in these mathematical models of cardiac cells, they do contain the proteins of interest that the drugs are binding to, that we're measuring in that early point in drug development. And so here's an example of what someone did, and this kind of relates to this, this example I'm going to talk about. So what you can do is you can take the input data, so the drug affinity for the ion channel, and then you can simulate this mechanistic model with that perturbation. And that mechanistic model actually gives a signal, right? So here's an example, I think, of like 80 odd drugs, right? So those original 50 drugs where we knew there was this simple linear input output behavior, add those extra drugs. And what you're seeing here is a model simulation of what we call an action potential. And this is the output from a mathematical model of a cardiac cell, right? So this is the signal that it creates, essentially, as a simulation. And what you're seeing here is what you call an action potential. And what you're seeing here is the action potential for all the 80 odd drugs that we were interested in. So what can you do with these outputs from the model? So this is the membrane potential. This is one of the outputs from the model. Another output from the model is something called the intracellular calcium concentration. So let's just consider this a signal. I'm not going to go too much into the biology here. So each of these simulations represents an individual drug, right? So you've got a signal, and what can you do when you've got a signal? As we know, we can create lots of features from the signal, right? So you can essentially create numerous things, right? So you could essentially look at the maximum membrane potential, the maximum calcium concentration. You could extract out some sort of derivative of this signal. You could extract out all sorts of measures, right? And in essence, I think this essentially heat map shows the number of measured. So they had 80 odd drugs in total, I think, in the end. And these are the number of measurements they were able to extract, right? So they extracted lots and lots of features from this simulated signal. What did they do? And so they use the machine. So you've got this input data, which is from experiments about the drug effect against an ion channel, individual ion channel. You simulate your mechanistic model, generate lots of information from the signal that comes from your mechanistic model. And then you combine that with principal components analysis and support vector machines to highlight that you have a really good model, right? So what they found here is that their best model in terms of ROC AUC, so area under the curve, gave a value of 0.96. But we knew there was a simple input output behavior, right? So by adding on this extra 30 compounds, did it really make a difference? And the answer is no, it didn't. So essentially what we found, so what I found is when I took their data set and essentially just built my standard simple linear model, which actually is mechanistic to a degree. So essentially it's designed looking at the simplest possible mechanism that could be used to explain the data. It doesn't really involve regression coefficients. We essentially give equal weights to the input data. You could get exactly the same ROC AUC value of a 0.96, whatever it is, by simply sticking with a linear input output model that we had before. So I guess that gives you an idea, I guess, to a certain degree of how it's actually quite easy to combine mechanistic modeling with machine learning and to fool a journal and to find a gullible journal that are prepared to take this. But it also highlights something else. It highlights that when you do have, so in this situation, let's be honest, they already knew there was a linear, the people did know there was a linear input output behavior. I mean, that was clear. It was known in literature because they did take drugs from that original study before they did this paper. But it also points to that there could well be, in situations where you're seeing this, these sorts of large sort of data sets up from that have not come from simulated data, but from real world data, there could well be heuristics in there. And those heuristics could well actually have some degree of mechanistic meaning, right? The trick is to find them. So this was a nice study in one way in that they started off with, they knew there was a simple solution. They didn't really tell people too much about it. They tried to add noise and then said, well, we can use mechanistic modeling combined with machine learning to then make predictions. But we have the information here, right? So we have the inverse problem. It's there. We have the solution to it here. So I think that's quite interesting that there could well be heuristics within these large data sets, but finding them is going to be hard, essentially. And for that, what I believe you need is good theory. I'm a big fan of good theory rather than just throwing algorithms onto data sets. primarily because I'm worried about, I guess, the data sets we're working. We know there's a lot of there's lots of information in the uncertainty in the variables. There's information when things are missing, they're missing for a reason. And understanding these things is quite hard when you're dealing with purely machine learning models, whereas it's not so difficult when you're dealing with statistical modeling techniques. So just to summarize, so I only planned for a half-an-hour talk, so I thought we'd have 50 minutes of questions, but just to summarize, so I guess data sets in my field, in pharmacology, they're increasing in size, that's clear. But we also know we have lots of noise, right? Not just in the input, but also the output, and also our prior knowledge. I talked about the fact we have irreproducible preclinical research. So a lot of people you're collaborating with, biologists, clinicians, anyone with a wet science background or even any other background, you really have to think about, well, how did they gain their knowledge? Were they basing decisions based on rejecting null hypotheses, so p-value tests, p-values, etc.? Were those experiments conducted correctly? We have an issue here of prior knowledge.